In 1977, humanity launched two daring explorers into the abyss, machines destined to rewrite our understanding of the cosmos. These probes, Voyager 1 and Voyager 2, were sent to uncover the secrets of our solar system, to peer into the unknown and bring back truths that would shake the foundations of science. They weren't just metal and circuits, they were emissaries of human curiosity, carrying our dreams to the stars. For nearly half a century, they've traveled unimaginable distances, over 24 billion kilometers, venturing where no human creation has gone before. Their mission was to photograph the outer planets, to study Jupiter, Saturn, Uranus, and Neptune. But they did so much more. They pushed beyond the boundaries of the sun's influence into the uncharted wilderness of interstellar space. And now, Voyager 2 has sent back a revelation so shocking, so profound, that it demands our attention, a discovery at the edge of our solar system that everyone has ignored for far too long. Imagine this: a lone spacecraft, older than most people watching this, drifting through the cosmic void, its faint signals taking nearly a day to reach Earth. It's powered by a decaying fuel source, its instruments clinging to life in the freezing, radiation-soaked depths of space. Yet against all odds, it's still talking to us, whispering secrets from a realm we can barely comprehend. Voyager 2's latest findings are nothing short of staggering, a confirmation of phenomena at the solar system's edge that scientists have overlooked, underestimated, or outright dismissed. This isn't just another data point, it's a wake-up call, a cosmic alarm bell ringing with truths that could redefine our place in the universe. What has Voyager 2 found? Why has the world turned a blind eye to these discoveries? And what does this mean for humanity's future? Buckle up, because this journey is about to blow your mind. Let's rewind to the beginning, to understand the sheer audacity of the Voyager mission. Launched in the late 1970s, these probes were built with technology that seems laughably outdated today. Their onboard computers have less memory than a modern key fob. They store data on 8-track magnetic tapes, relics of a bygone era, yet these antiques have outlasted every expectation, surviving the harsh radiation of Jupiter's orbit, the icy voids between planets, and the relentless cosmic rays of interstellar space. They were designed for a 5-year mission to explore Jupiter and Saturn, but a rare planetary alignment, happening only once every 176 years, gave them a chance to go further. With gravity assists from the gas giants, they slingshotted toward Uranus, Neptune, and beyond, embarking on what became the Voyager interstellar mission. This wasn't just a scientific endeavor, it was a testament to human ingenuity, a bold leap into the unknown. The Voyager's early discoveries were nothing short of revolutionary. When Voyager 2 reached Jupiter in 1979, it unveiled a planet more dynamic than anyone imagined. Its atmosphere churned with turbulent storms, plumes, and rotational patterns that stunned scientists. The Great Red Spot, a storm larger than Earth, was confirmed as a counterclockwise vortex. But what shocked researchers were the countless smaller storms littering the planet. They found 4 faint rings around Jupiter, defying the assumption that only Saturn had such features. And then there were the moons. Io, one of Jupiter's largest moons, was revealed as a volcanic hellscape, its surface erupting with lava lakes and plumes shooting 100 kilometers into space. This wasn't the cratered, dead world scientists expected. It was the most geologically active body in the solar system. Europa, another moon, hinted at a subsurface ocean, beneath its icy crust, a discovery that would later fuel speculation about alien life. Voyager 2 didn't just photograph these worlds, it rewrote the textbooks. Saturn was next, and Voyager 2's 1981 flyby was equally mind-blowing. The planet's iconic rings, once thought to be 5 broad bands, were revealed as hundreds of delicate ringlets. A new ring, the G ring, was discovered, and the F ring was shown to be kinked and multi-stranded, shepherded by 2 tiny moons, Prometheus and Pandora. Strange, ghostly spokes appeared in the B ring, defying gravitational theories and suggesting electrostatic forces at play. Saturn's moons were just as surprising. Titan, cloaked in a thick nitrogen atmosphere, was unlike any other moon in the solar system. Enceladus, a small icy world, was caught erupting, spewing water vapor, 10,000 kilometers into space, feeding one of Saturn's rings. These findings weren't just data points, they were glimpses into worlds that challenged everything we thought we knew. By 1986, Voyager 2 reached Uranus, a planet so remote it was barely understood. Its atmosphere was eerily calm, a featureless cloud deck that baffled scientists accustomed to the chaotic storms of Jupiter and Saturn. But the real shock came from its magnetic field, tilted 59 degrees from its rotational axis, a cosmic anomaly that defied all models. Uranus's rings, previously suspected but never imaged, were captured in stunning detail, along with 2 new shepherd moons. The probe also discovered 11 new moons, bringing the total to 16 at the time. Among them, Miranda stood out, its fractured surface marked by canyons 20 kilometers deep and bizarre, racetrack-shaped features. This tiny moon was a geological puzzle, hinting at a violent history of upheaval and reformation. Neptune, Voyager 2's final planetary stop in 1989, was a crescendo of discovery. The planet's vivid blue hue, caused by methane in its atmosphere, was breathtaking. Winds roared at 1,100 kilometers per hour, and a massive storm, the Great Dark Spot, raged with winds twice as fast, stronger than anything in the solar system. Neptune's rings, suspected but unconfirmed, were revealed as partial arcs, raising questions about their stability. Triton, Neptune's largest moon, was a frozen wonderland, its surface fractured and dotted with geysers, erupting nitrogen ice. Dark plumes suggested ice volcanoes, a phenomenon no one had anticipated. Voyager 2 discovered 6 new moons, cementing its legacy as a trailblazer. As it left Neptune, the probe turned for one last look. Its path bent downward out of the solar system's plane, heading for the stars. But the real bombshell, the discovery that's been ignored, came when Voyager 2 crossed into interstellar space. On November 5th, 2018, it became the second human-made object to breach the heliopause, the boundary where the sun's solar wind collides with the interstellar medium. This wasn't just a milestone, it was a plunge into a realm where the rules of physics are tested. The heliopause marks the edge of the heliosphere, the bubble of solar influence that envelops our solar system. Beyond it lies the interstellar medium, a soup of cosmic dust, gases, and charged particles from ancient supernovae. Voyager 2's instruments, still functioning after 4 decades, detected a dramatic spike in plasma density, 80 times higher than in the heliosheath, and a surge in galactic cosmic rays. These findings confirmed that the probe had entered a new frontier, but what it found next was utterly unexpected. Scientists had long assumed the heliopause was a smooth, well-defined boundary, like the surface of a bubble. But Voyager 2 revealed something far messier. The boundary is turbulent, filled with magnetic bubbles and fluctuations that defy our models. The heliospheric current sheet, a ripple formed by the sun's rotating magnetic field, compresses at the termination shock, creating these bubbles. This discovery shattered the idea of a clean transition from solar to interstellar space. Even more shocking, Voyager 2 crossed the heliopause at the same distance from the Sun as Voyager 1, 120 astronomical units. Despite occurring during a peak in the Sun's 11-year cycle, when the heliosphere was expected to expand. This suggests the boundary is far more complex and dynamic than anyone imagined, possibly twisted by magnetic turbulence from the Sun's birth in a supernova billions of years ago. Why has this been ignored? Because it's inconvenient. These findings challenge decades of theoretical models, forcing scientists to rethink the structure of our solar system's edge. They hint at a universe more chaotic, more unpredictable than we're comfortable admitting. The heliopause isn't just a scientific boundary, it's a cosmic frontier where the sun's influence ends and the galaxy begins. Voyager 2's data suggests we're surrounded by a turbulent, magnetic maelstrom, a region that could affect everything, from cosmic ray exposure to the stability of our solar system. Yet the world has barely noticed. Mainstream science has focused on exoplanets and black holes, while these groundbreaking discoveries from an aging probe are relegated to academic journals and obscure papers. It's as if we're too busy chasing the next big thing to see the cosmic truth staring us in the face. But there's more. Voyager 2's journey through the heliosheath, the region between the termination shock and the heliopause, revealed another ignored truth. The solar system's edge is a battleground. Solar winds, streams of charged particles from the sun, slam into the interstellar medium, creating shock waves and instabilities. The probe detected unexpected magnetic anomalies, suggesting that the heliosheath is a frothy, unstable region where magnetic fields twist and fold. This isn't just abstract physics. It has real implications. Cosmic rays, high-energy particles from distant stars, bombard the solar system, and the heliosphere acts as a shield. If the heliopause is more porous than we thought, more cosmic rays could penetrate, potentially affecting Earth's climate, technology, and even DNA. Voyager 2's data is a warning, a signal that we need to understand this boundary better if we're to survive as a spacefaring species. The emotional weight of Voyager 2's mission hits hard when you consider its fragility. This probe, launched when disco ruled the airwaves, has endured unimaginable hardships. Its power supply, a radioisotope thermoelectric generator, is fading, losing strength as its plutonium decays. By 2025, scientists expect it will no longer have enough energy to operate its instruments. Already, it's had to shut down heaters and non-essential systems, plunging its components into temperatures 70 degrees Celsius below their design limits. Yet it keeps going, a testament to the engineers who built it to last. In 2023, a miscommand tilted its antenna 2 degrees off Earth, nearly silencing it forever. For 37 agonizing hours, NASA waited, sending an interstellar shout from a deep space network dish in Australia. When the signal returned, confirming the probe had realigned, it was a moment of triumph, a reminder of how much we still depend on this lonely explorer. The stakes couldn't be higher. Voyager 2's discoveries aren't just about the heliopause. They're about our place in the cosmos. The probe's data suggests the interstellar medium is a dynamic, turbulent place, shaped by the violent deaths of ancient stars. This isn't a static universe. It's a living, breathing entity, and we're just beginning to understand its rules. The magnetic bubbles, the cosmic rays, the twisted heliopause. These are clues to a bigger puzzle. What lies beyond the heliosphere? Are there other boundaries, other forces we've yet to encounter? Voyager 2 is our only window into this realm, and its time is running out. When its power fails, we'll lose our only direct link to interstellar space, leaving us blind until new missions can be launched. A process that could take decades. This brings us to the heart of why Voyager 2's findings have been ignored. Fear. Not fear of aliens or cosmic disasters, but fear of the unknown. Humanity has always struggled to confront truths that challenge our worldview. The heliopause isn't just a scientific concept, it's a metaphor for our limits. It's the edge of what we can control, the point where our sun's power fades and the galaxy takes over. Voyager 2's data forces us to face our smallness, our vulnerability in a universe that doesn't care about our existence. It's easier to focus on earthbound problems or glamorous space missions than to grapple with the unsettling reality of a turbulent cosmic frontier. But ignoring this truth won't make it go away. The heliopause is there, and it's more complex, more dangerous, and more fascinating than we ever imagined. Let's talk about the human side of this story, because Voyager 2 isn't just a machine. It's a symbol of our dreams. When it was launched, the world was divided by the Cold War, yet scientists from across the globe united to make this mission possible. They packed the probe with a golden record, a message to any intelligent life that might find it. This record carries the sounds of Earth, whales singing, babies crying, Mozart's music, and greetings in 55 languages. It's a snapshot of who we are, a plea to be remembered. Imagine the hope it took to send that record into the void, knowing it might outlast our planet. Voyager 2 isn't just collecting data. It's carrying our story, our legacy, into the stars. Every signal it sends back is a reminder of what we're capable of when we dare to dream big. Now let's dive deeper into the science, because the details are where the real shock lies. Voyager 2's plasma wave detector, one of its few remaining instruments, has been crucial in mapping the heliopause. When it crossed the boundary, it recorded a sudden jump in plasma density, from the sparse solar wind to the denser interstellar medium. This transition wasn't gradual. It was abrupt, like stepping from a quiet room into a roaring storm. The probe also measured a spike in galactic cosmic rays, particles accelerated by distant supernovae. These rays are a double-edged sword. They carry information about the galaxy's history, but they're also a threat, capable of damaging electronics and mutating DNA. Voyager 2's cosmic ray subsystem, still operational despite the odds, has shown that the heliosphere filters out fewer rays than we thought, raising questions about how well it protects Earth. The magnetic field data is even more perplexing. Scientists expected the magnetic field to shift dramatically at the heliopause, reflecting the influence of interstellar stars. But both Voyager probes found no such change. The magnetic field remained aligned with the sun's, suggesting that the interstellar medium near our solar system is heavily influenced by our star's ancient history. One theory is that the sun formed in a hot, ionized region after a supernova, and the magnetic turbulence from that event still lingers. This would mean the heliopause isn't a clean break, but a tangled web of magnetic fields, stretching far beyond what we can measure. Voyager 2's magnetometer, a marvel of 1970s engineering, is giving us a glimpse of this cosmic tapestry, but it's a fleeting one. When the probe's power runs out, this window will close. The implications are staggering. If the heliopause is as turbulent as Voyager 2 suggests, it could affect how we plan future space missions. Interstellar travel, a dream of science fiction, will require shielding against cosmic rays and magnetic instabilities we're only beginning to understand. The heliosphere's shape, once thought to be a comet-like bubble, may be more irregular, twisted by external pressures from the galaxy. This could influence everything from satellite design to astronaut safety. And on Earth, a weaker heliospheric shield could mean more cosmic rays reaching our atmosphere, potentially disrupting climate patterns or increasing mutation rates. These aren't abstract concerns. They're real risks that demand attention. Yet the world remains distracted. Social media buzzes with memes and trends, while Voyager 2's revelations barely make a ripple. Part of this is timing. Launched in an era of analog TV and rotary phones, the Voyagers feel like relics, overshadowed by flashy new telescopes and Mars rovers. But their age is what makes their achievements so extraordinary. These probes have survived asteroid belts, planetary radiation, and the crushing cold of interstellar space. They've sent back images that inspired generations: Jupiter's storms, Saturn's rings, Neptune's blue majesty. And now, at the edge of the solar system, they're revealing truths that could shape our future. To ignore them is to turn our backs on our own potential. The emotional pull of Voyager 2's mission is impossible to overstate. Picture the scientists who built it, pouring their hearts into a project they knew they might not live to see completed. Imagine the engineers, now in their 70s and 80s, still monitoring signals from a probe they launched as young dreamers. Think of the countless schoolchildren who gazed at Voyager's images in awe, inspired to pursue careers in science. This mission isn't just about data, it's about hope, resilience, and the unquenchable human drive to explore. Every beep from Voyager 2 is a heartbeat, a reminder that we can achieve the impossible when we work together. To let these discoveries fade into obscurity is to betray that legacy. So what's next? Voyager 2's days are numbered. By 2026, its power will likely fail, and it will drift silently through the cosmos, a ghost ship carrying humanity's message. It will take 40,000 years to reach a star in the Camelopardalis constellation, and 296,000 years to pass Sirius. Long after Earth is gone, Voyager 2 will endure, a testament to our existence. But we don't have to wait for the future to act. The probe's data is here now, demanding we listen. We need new missions to follow in its footsteps, probes equipped to explore the heliopause and beyond. We need to invest in understanding the interstellar medium, not just for science, but for survival. The galaxy is calling, and Voyager 2 has given us the first words of its language. This isn't just a story about a spacecraft, it's a story about us. Voyager 2's discoveries at the solar system's edge